inverse trig functions give us a way to solve for a trig function. For example, if we have y is equal to sine of x and we want to solve for x, we know that sine of x will go from -1 to 1. Well, actually, I guess it's better to use this in notation because those endpoints are included. The inverse function would be known as arc sine, or sometimes it's written with a -1. So if we're solving for x, arc sine of y is equal to x, because we would apply it to both sides, and the arc sine and the sine would cancel out and just give us x. The sine wave goes from -1 to 1, but it is not always 1 to 1. On one period it is. We have to restrict their domains, and then the function becomes 1 to 1. Typically, this will be from -pi/2 to pi/2, which when you graph it will look something like this. Add pi/2, it's equal to 1, and minus pi/2, it's equal to -1. So this is our sine of x graph. Our inverse sine graph is very, very similar to this, but now we change our points around a little bit. It's the same shape, but now we have 1 pi/2, -1, comma, -pi/2. And these are still x and y. One easy way to look at it is that the domains and ranges get flipped. I'm going to erase this to make it a little more legible. Make that in red maybe. These are all pi's. So for sine of x, our domain on our restricted range is minus pi/2 to pi/2. And then the range is -1 to 1. For inverse, we flip them. Our domain, -1 to 1, and our range is minus pi/2 to pi/2. Just flipperoo. One interesting thing about inverse functions is that if we were to plot them together, we can also have the line y is equal to x, which is its own inverse. And if you were to graph them together, you would see that they're reflections about this line. It would look something like that. This isn't the best drawing. Something like that. Not the best drawing, but this is kind of the general idea. We can also take the derivative. An example, the derivative of sine of x is cosine of x. If we plot sine of x, imagine that's a perfect sine function. At that peak, we have pi/2. Let's see, we're finding the slope right there. Let's imagine that's a straight line. So let's say we're doing the point 3 pi over 4. The function value would be root 2 over 2. And because it's cosine of x, we could plug that into our function, and it's negative root 2 over 2. And we can actually write the line now. Y minus root 2 over 2 is equal to minus root 2 over 2 times x minus 3 pi over 4. And after rewriting, oops, this has a root 2 over 2 also. So one thing that always tripped me up was, oh look, we can draw this tangent line. Imagine that's tangent, and these lines are supposed to go on forever, and it looks like it crosses at 2 different points. So like, how can that be a derivative? Well, there's a couple things. First, it's intercepting it, and it's a tangent to the curve locally, and second, it shares the slope of the curve at that specific point. So that is what means that's what makes it the derivative, is that it's tangent at that point and also sharing the exact same slope. Anyway, thanks for watching.